There are a lot of distinct properties in the structures of graphs that extend beyond the idea of matchings. I've jumped chapters, and we didn't do chapters 9 and 10 and 11. We moved around a bit. But some of the interesting properties of a graph can be found in ideas about the way in which one draws the graph in the first place. But, like containing a matching, containing particular factors, containing peripheral sets, boundary sets, all of these vertices, we can look at these subgraphs and properties about them. One of them is the idea of domination and dominating sets. Pick a vertex. Well, what's our definition of a neighbor? A neighbor of V and N of V, the neighborhood N of V is the set of all neighbors. Now, in some graphs, that could be a disconnected set. Because what's missing from that set that would connect all of those things together? V itself. I'm only looking at the neighbors of V. V is not its own neighbor. There's no edge from V. We're in a simple graph, no loops. So I'm going to make a note here, and I'm going to call this the open neighborhood of V. And if I include V, that's a closed neighborhood. Okay. We talked about an edge covering and a vertex covering, an edge cover and a vertex cover. What were those things? So I thought about edges covering the vertices they hit. I talked about vertices covering the edges they hit. I'm going to say that V, in some sense, covers its neighborhood. But instead of using the word cover, I'm going to use the word dominates. We say that V dominates its closed neighborhood. Or V is a dominating vertex for those other vertices, which means V dominates a total of 1 plus the degree of V vertices. Why 1 plus? I'm including V itself. The degree gets all of the open neighborhood, the 1 plus gets V itself. All right. So what's a dominating set for a graph? I want to dominate the entire graph. Like an edge cover covers all the vertices, like a vertex cover covers all the edges, I need a set whose members dominate all vertices in the graph. Wait a minute. A vertex dominates its neighborhood. So I'm really saying I need you to pick a set of vertices whose neighborhoods cover the graph. Closed neighborhoods. But since the closed neighborhoods are the vertices themselves and everything adjacent to it, another way of saying this is that S is adjacent to everything else in the graph. Is the following set of vertices a dominating set? Why? So that's these four. They're covered in the neighborhoods of U and V. And then that's all 7 vertices that are outside of the set S. We've dominated everything because every vertex in V of G minus S is adjacent to some vertex in S. I would like you to find me another dominating set. Let's play name that subgraph. I can do it in 3 vertices instead of 4. UVW. Question. Can you do it in 2? Or another question, is that the only set of size 3 that works? At the moment, all I can say with certainty is I haven't found 2 vertices that dominate everything. But 7 choose 2, 21. There are a lot of options, aren't there? And I don't know if there are more sets of size 3 that do the job. So I don't know the answer to either of those questions, but I know I can do it in 3. If that is the smallest one, I'm going to call it, based on all the history of the others we've called, a geodesic measures distance from a particular vertex to a particular vertex. I'm talking about a whole set of things. I'm pretty sure I'm not going to call a set a geodesic set. Minimum dominating set. Okay. Once I figure out what that minimum cardinality is, just like with our edge cover and our vertex cover and our independence, we had a number. Once I know the smallest possible number of vertices needed, I'm going to call that the domination number of the graph. Now, an interesting note is that I've run out of symbols. That's the lowercase Greek letter gamma. But gamma is also used in a different way to talk about the genus of a graph. But that's in chapter 9 and we skipped it. Genus is a way of measuring the complexity in terms of the way you draw the picture. So, a short diversion. If you can draw your graph on a flat piece of paper, that's genus 0. If you can draw it on the surface of a ball, that's genus 0. Because technically, there's a one-to-one and onto map from the surface of a ball to a flat sheet of paper. It's called stereographic projection. It's the way you make good maps. Unfortunately, it really distorts the snot out of things. But some graphs can't be done that way. And my favorite example is K33. What's K33? Bipartite, complete. So 3 dots on one side, 3 dots on the other side, connect all dots to all dots only from one side to the other side. I claim, no matter how you try and draw that on a sheet of paper, you have to cross the lines. Have to. But I have in my office a coffee mug with 3 houses and 3 utilities: gas, fire, electric. You have to connect the fire station, the gas station, and the electric station to all 3 houses without crossing the wires. I just said you couldn't do that. What's different about a coffee cup? It's got a handle. There's a hole in that surface. If I use the handle, I can pass one wire over another without crossing them. That's genus 1. I need a handle to not cross the strings. Genus measures how many handles you need to uncross everything. If you can draw it flat, genus 0, then there's never going to be a K33 in your graph. No subgraph can be like K33. Nor can there be a subgraph like K5. K5 can't be drawn flat without crossing stuff. Proving those is amazingly neat, very cool, and beyond what I'm doing this semester. So that's all I'm going to talk about genus. There's a lovely topology discussion in there and more chapter 9 stuff, and we might mention it again next semester in readings. Interestingly enough, domination in graphs is a recent development. Some of the major papers in domination of graphs are as recent as 1998. The idea itself only goes back to the early 1960s, late 1950s. So this is a 70-year-old idea, not a 200 or 300 or 400. This isn't even as old as, Eulerian. Eulerian's 200 and some odd years old. This is only 70. Young for math. Okay. I claim every graph has a dominating set. I claim it. You should prove it. By the way, this proof is one line long. I just take all the vertices. But I agree with you. That is lame. Come on. So I know I have a dominating set. The question is, can I find a smallest dominating set? Can I find this minimum dominating set? And that means that if the graph is of order n, my domination number is somewhere between 1 and n. Okay, so let's look at the extreme case. When is your dominating number 1? So there's got to be a vertex whose degree is? There you go. If you've got one vertex of degree n minus 1, then its neighborhood is every vertex. Its closed neighborhood is every vertex. And therefore, I know what my minimum dominating set is. It's the vertex of degree n minus 1. It's any vertex of degree n minus 1. Go to the other extreme. When is your domination number n? Because then every vertex can only cover itself. Every vertex has degree 0. I'm going to use a bar on top of neighborhood to indicate closed neighborhood. I'm stealing that notation from topology. A closed set. We did that in Calc 3 as well. Talked about closed disks with a little bar over them. The other way to think of that is to say, oh, my graph has no edges at all, right? So it's the complement of Kn. And unfortunately, that's where I use the same symbol for two different things in the same sentence. Okay. I want to go back to this example for a minute. I know the domination number is at least 3. Might be smaller, at most 3. How can I show that the domination number is 3 here? Because S prime at 3. I need the closed neighborhood of 2 vertices. Cover all of the vertices. There are 11 vertices. So the total degree of those 2 vertices has to be 9. How do I know I can't have that? The highest degree is 4, so if I took any 2 vertices, the most I could get is 8. I can't do it in 2 vertices. I know I can do it in 3 or fewer. Well, then I got to be able to do it in 3. Questions? Get to ask the best one then. Why? Why on God's green earth do I give a flying and a rolling donut about this? What could this possibly do for me? Let's make a grid. Here's a grid, 3 rows of 4 vertices. Unfortunately, it is 4 years ago, I believe. There was a talk, the MAA, that was done on Zoom, and we showed it in Lynch 106, called Art Galleries and Sleepy Gardens. Let's assume that this is a set of city blocks, and I want to put the cops so that they can cover all the blocks. Where do I put the cops? A cop can see to the next intersection in a straight line. How many cops do I need to cover the beat? I certainly can do it with 12, but can I do it with fewer? I'm cheap. I don't want to pay a lot of overtime. Well, if I find a minimum dominating set, then every vertex is adjacent to a vertex with a cop in it. The cops can cover all the roads. Find one. Find me any minimum dominating set. By the way, this is a product, a Cartesian product of sets, right? It's a path of length 3 times a path of length 4. I claim I can do it in 4. I'll give you a hint. No corners. Abigail, you were dawning. Did you find one? I'm sorry? I certainly can do the middle 4. If I do the middle 4, I absolutely get top 4 and the bottom 4 right away. Yes? Do I have to do just a row across the middle? Jonah, was that what you came up with as well? But yes, that absolutely works. And that means I know that the domination number is 4 or less. Now, I started the same way you did. I said, hey, wait a minute. If I start in the middle over there, Well, then I don't need the one in the middle next to it, do I? Because that's dominated by the one on the end in the middle. So if I use this vertex in my dominating set, I'm not required to keep this one. And if I use this one, then I'm going to miss here. So let's use this one. And that covers here and here. But it doesn't cover here. Oh, and it covers here. How do I cover this one? Well, I can use this. What vertex is still left undominated? Say again? Middle row. So I did it with 4, but I did it with a different 4. But I can do it in 4. What I have to prove now is that I can't do it in less. It's very difficult to prove you can't do something. What's my best method of proof for this? Proof by contradiction. I'm going to say, okay, let's suppose we can do it in 3 and see what we F up. That graph has another interesting property. The interesting property is that graph is bipartite. Ah, sure it is. How the hell do you know that? I don't off the top of my head, but I can show it's bipartite. Ready? Pick a color. Say again? We're going to color some vertices green. So I'm going to cover this first vertex in the upper left corner green. Well then, the next vertex should be not green, adjacent to that. So those are not green. Adjacent to all of those, take one more step. Green, green, green. Take one more step. Not green, not green, not green. Take one more step. Green, green. Take one more step. And by the way, I don't care what corner you start at. Doesn't matter. Notice what we have is diagonal rows. Every diagonal is a different color. They alternate back and forth. Great, fabulous. So what? All right, wait a minute. Give me one other piece of information. Let me give the degree sequence. What's the degree sequence for this graph? Write down the degrees. Which means there are 2 4s and 4 2s, the corners, and the rest are 3s. Great. Well, wait a minute. That means 2 vertices dominate 5 each. So if I were able to use those first 2, dominate 10 vertices with just those, right? And if I take the next one, that's 14 vertices. So if I can use, or even if I just used one of the 4s and 2 of the 3s, that would be 5 and 8. That's 13, because it's 1 plus the degree of v. So it is reasonable to say maybe I can do it, because the sum of the degrees is big enough in the dominating set idea. Gives 10 plus 3 is 13. I can actually stop the arithmetic. Okay, so maybe I can do it in 3. It's not ruled out by my degrees, right? All right. But if I'm going to pick 3 vertices, notice that in every neighborhood of a vertex, what do you notice about the colors? Say again? They're only adjacent to the opposite color. So, if I had a dominating set of 3 vertices, 3 is odd, 2 of them have to be the same color. It could be that all 3 of them are the same color. But let's suppose that all 3 of them have the same color. If all 3 are the same color, why do I know that's not a dominating set? Actually, let's take that out. In any set of size 3 vertices, any set of vertices, any 3 vertices, if all 3 vertices are the same color, it can't be a dominating set. Why? I'm going to miss all 3 of the other vertices of that color, because everything I'm adjacent to, if all 3 of the ones I pick are green, then the other 3 are all not green. Crap. If the 3 I pick are not green, then all of the vertices they're adjacent to are green. Damn it. All right. So there's a way I can't have a dominating set. So 2 vertices are one color, and the third one is different. Then I'm going to run with it. We'll make the two vertices green. Okay. If this lone vertex has degree 3 or smaller, then it dominates at most 3 of the red vertices. Why is that a problem? I dominate 3 of them, and then I picked 2 for the other. I'm not going to pick the 2 I miss a green vertex. So here was a problem. Here's a problem, which means what do I know about the not green vertex I pick? Can't have degree 3 or smaller. It's got to have degree bigger than that. Which means it's got to have degree 4. Wait a minute. Go back and look at the picture. There is only one vertex of degree 4 that is green. That one. And there's only one degree 4 vertex that's not green. We just said the not green vertex has to have degree 4. This one is officially part of my set. So far, so good? I have to pick 2 green vertices, yes? I've dominated 4 of them. The other 2 vertices I have to pick are which 2 vertices? The ones on the left edge. Those are the only 2 green vertices that are not already covered. Once again, Houston, we have a problem. What did I miss? 2 white vertices on the right edge are not covered. No matter what set of 3 vertices I try and pick, I fail to make a dominating set. it's bigger than 3, less than or equal to 4, it's got to be 4. More domination on Friday. See you all.